Good morning, good morning. It's great to see you. No, that's like the orange juice song, like where the oranges are like jumping into the bottle. Yeah, yeah, for the orange juice commercial. All right, well let's get to it then, shall we? So let's go back to the Elgato and so I don't think I did a very good job last week of explaining branching, linking, branching and linking, conditional branching, etc. So let's look back at it. So let me, first off, I'm going to copy project over to my projects directory. Okay, so now I've got two different branch link examples. So what I'd like to do is, well, first off, we'll open up Genie. And let's open main.asm. Okay, so we'll start here. Okay, so I'm going to make one quick change here, and we'll talk about why it will get stuck in a moment. Okay, so I've got a really simple, let's see, I'm going to get rid of this. Let's make that 3. All right, just want to make a couple of minor tweaks here. Okay, so I've got this program that I wrote that's not going to do anything in particular. It's just going to load in the number 3, and then I wrote 2 subroutines, one of which will double the number and the other which will square it, just to do something. And what I wanted to talk about was the difference between branch and link. Okay, so first off, the branch or branch and link instructions, both of them are unconditional. Okay, meaning what? Okay, so what do we mean by conditional versus unconditional branch? Hmm? Yeah, checks flags or doesn't in the case of unconditional, right? So an unconditional branch is going to branch regardless. Okay, regardless of what happens to the flags or whatever. So it's a forced jump. Um, and what is it going to jump to? Well, in the assembly, okay, so where I've got either B routine 1 or BL printf or BL routine 2, whatever, okay, in both cases, what have I specified? I specified a label, okay, of what routine I wanted to jump to. Okay, so in this case, I've got the routines that I've written called routine 1 and routine 2. But I'm also in 2 different instances going to branch to the function called printf, which is part of the C standard library, right? That all that's going to do is print stuff to the console. Okay. So that's sort of an output function that we can use. So I don't have to write the code for printf. This is why we have to use GCC to link things together, because we're making use of something from the C library. Okay, anyway, so what I want to talk about really is the difference between branching and linking, okay, and kind of see this in action. Okay, uh, so what I did was to sort of deliberately make us realize what's the difference between the two, is that for routine 1, I just used a branch. For routine 2, I used a branch and link, okay? And routine 1 and routine 2 are basically the same. The only difference is one of them just doubles the number and the other squares it, okay? There's nothing special about the routines. I just wanted it to do something and have the output from each of those be different so that we could tell which one that we had run. Okay, so that's all that's going on there. Okay. Okay, so first off, let's assemble all this and start looking at the listing file and see what's going on. Okay, so save that, get myself a terminal window. Here, and I'll kind of scoot it over there. All right, so let's see, we need to go to projects. We need to go to branch link without the hyphen. Okay, and then in this case, I'm going to go ahead and reassemble everything because I made a few changes a minute ago. So I'll do that. I'll do AS-A to get my listing file. And then actually I'll just go ahead and do the debugging version. And GCC. And then I'll remove this a.out file. Okay, so now we've got everything we should need. So let me open up the listing file in Genie so it's a little bit easier to read. And let's just go through what we've got in front of us, okay? So because I'm using printf, I have to have a formatting string, and I think we talked about that last time. What does the format string need to look like? Well, in this case, I'm just having it output that says the number is, and then whatever the number is. And so my string is, well, the number, the part with the English is kind of whatever I want. But then what is this part, the %LLI? What does that say? What does that mean? Right, okay, so what am I outputting? What kind of data? I'm outputting a number, okay, but what kind of number? A 64-bit integer, okay? And how am I going to format that? Well, am I going to output it in hex or in decimal? Or, well, we already talked about that you can't do it binary. Am I going to output it in hex or in decimal? So base 10. In this case, which one? It's decimal because that's LLI. If I wanted it in hex, it would be LLX. Okay, so the type of data that I'm outputting, or the particular object that I want to output is in this case just a 64-bit integer. Okay, so something that's going to be sitting in one of the X registers, whatever it is, okay? And I want to display it as just a regular base 10 integer, nothing fancy looking, okay? Um, and then what about the \n that's at the end of the string there? Yeah, all that's going to do is basically hit enter after the output so that the next time that there's an output, it'll be on a separate line, okay? Okay, and then while we're at it, let's kind of look there in the hex for our listing file. So what's going on over there to the left of where the string is? So we've got that big long 4E7556D. Sorry, did I miss one? 4E756D62 blah blah blah. Okay, so what's all that jazz? So let me highlight it. what is all of this nonsense right there? Huh? Code in what sense? Yeah, it's the ASCII for the string. Okay, so we bust out an ASCII table, right? What is for E? It's capital N. What is 7.5? Lowercase u. 6D is M. 6.2 is B, etc. Okay, and then the what's at the end of this thing? What's got to be at the end of a string? Yeah, it's the null terminator. Okay, so you just in C at least, uh, your strings are terminated with 00, a single byte, right? Because in ASCII, every character takes just one byte, which is kind of nice. Um, and okay, so that gets us the um, sorry, lost my train of thought for a minute. Um, right, that terminates the string. And so if you were reading a string byte by byte, how would you know that you've gotten to the end of it? Well, you just look for the null terminator byte at the end. Okay. All right, so that's my formatting string. And I've got the parts that are important, right, are the this is going to tell printf that I want to output a 64-bit integer and how I want it displayed. And then the \n is going to tell printf, hey man, hit enter when you're done so that the next output would be on a new line. That's all. Okay. Okay, so are we Gucci with that part? Right? Okay, it's just encoded in ASCII. And where do you find the ASCII encodings? You just look it up on a table, right? So Google ASCII table, and bam, there you go, right? In particular, uh, what is 0A on the ASCII table? I don't remember. So let's go look. Let's consult the bastion of all knowledge of Western civilization. All right. So, that's what 0A does. New line. Okay, that makes sense, right? Okay, learn something new every day, huh? Okay, so anyway, so there's our string, Gucci. Um, and okay, so then let's go back down to the other business, right? So let's look at here this instruction. Okay, so branch routine 1. Okay, which is 0A 000014. Okay, great. So let's decode this thing. All right. So the first thing that I've got to do is let's look at well, what all do I have in it? So zero. Well, okay. So actually, let me just copy this for a moment. Okay, and then I'm going to go down to. I'm just going to open up a Scratch, basically a blank file, just so I can type something in it. All right. So what's the first thing we got to do to decode this thing? Hmm? Porter, You're doing the like, huh? The John Madden, right? Like drawing on the screen, right? And the tight end's going to come over here, and the okay. So what do we got to do, right? The Indianness problem. Okay, so what's the issue here? For us to understand this thing, we need to reorder it, right? So how do I reorder this one? Take it two or one byte at a time in order for the bytes, okay? So what I mean by that is, right, each pair of hex characters is a byte, okay, because each hex character is a nibble, which is 4 bits. Good? Okay. And so I've just spaced it out there in terms of its bytes, and then I take those bytes in reverse order. But I'm not flipping the entire thing around. So the the last byte is 1-4. That becomes the first byte. The first byte is 0A. It's still 0A, not A0, right? So you flip around the bytes, but not within the bytes. Does that make sense? Yeah. Is it too early? Or are we all like dead? All right. What time did everybody go to bed last night? 12:30. Evan? Huh? Oh, jinx. Yeah. 3 a.m. Well, you should at least get in the bed and turn out the lights. Even if you lay there for 3 hours, you are more rested than if you. Oh, well, take an Ambien or something. I don't know, right? Um, okay. So anyway, uh, yeah, Jax, you have a good weekend. Uh, the Okay, so we had to reorder it right for the decoding part. Okay, and then what we need to do is go to our handy dandy, um, where did I put it? This guy, our Excel sheet that's got all the decodings, and then we'll figure out what's going on with it. Uh, okay, so we'll see what's going on there. Oh, this was the little, yeah. Okay, so I'm not sure why it didn't open it. There we go. Okay, so here's our thing, and well, we already know what instruction we've encoded, right? It was the B, the branch instruction, so we just have to find that in here. Okay, so and there it is, right there. So I'll blow this up so that we can see it a little bit better. Um, okay, so we've got the branch, unconditional branch, immediate, right? So um, we've got the B and also the BL, which we'll talk about in a minute. Okay, but let's look at the encoding. So what do we have in our encoding? Well, we have, you know what, I'm going to hide this, um, these columns, just to make it a little easier to see. All right, so what do we have here with the branching instruction in terms of its encoding? Well, actually, two things to notice is that what's the difference between the branch and the branch and link? Well, not necessarily negative, but its first bit is a 1 versus a 0. Okay, so the only difference between branch and link in terms of its encoding is this very, very first bit, whether or not it's a 0 or a 1, okay? And we've actually seen plenty of instances of that where the first bit, right, often the first bit was what told you whether or not the instruction was dealing with 32-bit data or 64-bit data, right? So when we had the move instructions, that first bit was what told you which it was. Okay, so that's kind of nice that the encodings are essentially the same, right? So opcode 1.4 basically for well, not quite 1.4. It could be slightly different, but probably 1.4 and 9.4. It's all going to depend, obviously, on this immediate 26 field. Okay, so immediate 26 is therefore how many bits? Huh? Yeah, last time I would check, that would be 26. Okay, and right, so we're going to have 26 bits there that are basically where we encode the label. Okay, so let's go back over to our other thing, and let me just copy. We've got this here, right? So it'd be 1.4. Okay. So where did I have? I was doing this in Genie. Okay. So the 1.4. Oops. The 1.4 is really that, right? Okay, in binary. Okay, and really what I should do is I should look, well, let's go back to our, sorry, our sheet here, because it was 6 bits, okay? So 0001, okay, and then 01 something. Okay, so there's the 6 bits, and then everything that follows that is going to be our immediate 26 value. Okay, good. All right, what was our particular immediate 26 value in this case? Well, what do you think it's going to be? Bueller. Well, okay, here, let's do this. Write this in binary. 1, 4, 0, 0, 0, 0, 0, 0, or so A is 10, so an 8, that. Okay, that is, let me get rid of this space. That's that, just in binary, right? All right, so what's the immediate 26? It'd be all of this stuff right here, right? The last 26 bits. Yes? Okay, so our immediate 26 value here is just A, right? In fact, let me just say A. That's it. Oops. Okay, what is A in decimal? 10. Okay, so 10. 10 shall be the number of the immediate, and the immediate value shall be 10. Rocking the Home Depot today. Yeah. You can do it. We can help. Or let's do this. Right? That could be the Home Depot commercial guy. Yeah. Huh? Yeah, probably gets paid a little more than you do. All right, so our immediate value is A. Now let's go back to the listing file and see what the hell A is supposed to tell us anyway. All right, so where are we? We're on this line, okay, line 13. And at line 13, the program counter's value would be 8. Okay, that's the bit in the beginning there. Okay, and why is it 8? Well, because it's the third instruction, right? And each instruction takes how many bytes? 4 of them. Okay, so the program counter increments by 4s. Okay, so where are we supposed to jump? To routine 1. Where does routine 1 begin? On line 26, or program counter value, because that's how everything really is, 3, 0. Okay, good. So what is our immediate 26 value? It's A. Isn't this thing supposed to be pointing to routine 1? So would you expect that instead of 0A, we should have seen 3, 0? Because that's the program counter's value, or would be the program counter's value, in order for us to read that the instruction at program counter value 3, 0. Okay, so would you expect that? Yes or no? Does it make sense why it ought to be that? No, it does not. Okay, so I've got, so good question, right? So the line numberings here, um, either in the file or in Genie, right? Because there's two separate line numberings going on. So like, for example, line 2, 3 and 2, 4 here are blank, right? But in terms of the executable, those don't exist, right? What exists in the executable? Just the instructions, okay? So to determine how far we're jumping, all we've got to do is look at the second column here where it's got the stuff in hex. So 0, 4, 8, C, 1, and so on. Okay, so what's going on there? It's incrementing by 4 each time, because in this architecture, how long is every instruction? 4 bytes. Okay, that's nice, I think. Okay, good. So if we're to jump from 0A to 3, 0, okay, how much do I need to, so these branching routines, they're program counter relative, meaning, so let's actually go back to Brookshire for a moment. How did jumping work in Brookshire? You had the B opcode, then you specified which register got compared to 0, and then what did you specify? You specified a memory address, okay? So if you wanted to jump to the instruction at memory address A0, you put A0 there. Okay, regardless of what your program counter's value was. Okay, branching on ARM is program counter relative, well, with the B instruction anyway. Okay, so what that means is that rather than saying the exact address that I want to jump to, I'm going to say, how far is that address from where I am right now? Okay, does that make sense? The difference? Okay, so, but here's where it gets interesting. So you counted the number of lines, didn't you, just then? Okay. Well, that was coincidence. Okay. So, um, good observation, right? So, what Evan just noticed was, how many lines of instructions does it take for me to get from where I have the branch routine to where I have the actual beginning of the branch, I mean, of the routine? It was 10, or 0A, instructions to get there, okay? So that's what we've encoded. But what I need to say is how to change the program counter to do that. Okay, what's the difference between the program counter from 0A to 3, 0? Yeah, no, I'm sorry, I meant 08. Yeah, thank you. Yeah, okay, so the line that's highlighted, 08, okay, that's the program's counter's value at that instruction. Okay, what's the program counter's value need to be for the instruction to which we're jumping? It would be this one, right? So what's the difference between 08 and 30? Well, think carefully. In decimal or in hex, first off? Well, in hex, what's the difference? 2, 2, because subtraction still works the way you think it ought to. Okay, what is 2, 2 as a decimal number? Uh, well, okay, let's just not be idiots and let's just write it down and make sure that we're not being idiots because it's too early in the morning. And all right, so what was it? 30 and 08? Okay, and I want to do minus. So we'll go back to grade school. All right, so can I take 8 from 0? No, so I have to borrow a 1 from the 3, and that makes this a what? Well, a 16, right? So let me write that as a 1, 0. Okay, if I take away 8 from 1, 0, then I get 8, right? Yeah, okay. All right, so I get uh, 8 in that position, because really I'm going to think of this as being 0, 8, right? And then what's, yeah, so by 2, 2, I meant 2, 8. Yeah, it's too early in the morning to do arithmetic. Okay, what is that as, so let me write this as a hex number. Oops, dang it. What is that as a decimal? 40. Okay, Gucci? All right, let's double check and make sure that we're not complete idiots. So what was it, 30 and 08, or 30 rather? What is that in hex? Or sorry, this is a hex number is what in decimal? That's 48, and that's 8. And so the difference is 40. Okay, so the difference in hex is 28, and the difference in decimal is 40. Okay, good. But what was encoded? A. So how do I get from A to 28? Okay, times 4. But what's another way of doing times 4 in a binary machine? Bit shift twice, exactly. Okay, so what happens is that when you load this immediate 26 value, okay, in this case, what was our immediate 26 value? It was these 26 bits. So let me copy those down here, okay? And then I'm going to put in a little bit of spacing here. Oops. Let me get rid of the spaces. Okay, good. So that's the immediate 26, all right, that we had. So what's going to happen when this instruction gets executed? We load in the immediate, the 0A, okay, and immediately bit shift it 2 spots to the left. Why should we have done that? Well, because how many bytes does each instruction take up? right? So if it's 10 spots, but each spot is 4 bytes, then we need to shift by 40 bytes, not 10 bytes. Hmm? ARM? No. No, I'm pretty sure that every instruction is 32 bits, which is nice. Oh, yeah. Not all architectures have same length instructions. So the 6502 definitely is variable length, which would make this kind of a pain because um, you would have to know how how many instructions you had and kind of count everything up. Okay, so the immediate 26 is going to get bit shifted to be, well, here, let me just copy everything. Let me just copy that. And it's going to be shifted over like so. Okay, so this would be the M26. And then what's the symbol for shifting left twice? Or how do you do bit shifting? Do you guys remember from Java or C? Oops. That. Okay, so do you guys remember the bit shift symbol? Did you guys ever do this when you were in 111? You never did bit shifting? Ah, huh? Was a wild ride? Okay, well, well, okay. Yeah, maybe you didn't run into it in 111, but what about in 211? Those of you who have taken it, data structures. No? All right, well, that's fine. We'll just do it now. Okay. So, uh, the bit shifting operators, there's two of them. Okay. Because which directions could I shift? I can shift left and right. Okay. And in this case, I'm bit shifting to the left, which is paramount, or well, bit shifting by one position to the left is like doubling the number, right? Okay. Bit shifting one to the right would be like having the number and discarding any remainder, if there was a remainder. Okay. Um, and in C, and I suppose it's probably the same in Java, the operator to do this is the double less than symbol, or for bit shifting to the right, the double greater than symbols. Okay. So if I took a number, okay, so I've got my 64-bit number here, and yeah, I've only written 26 bits, but what are the rest of them? They're all zeros. Okay. If I bit shift that 2 positions to the left, then what does it do? All the bits just shift 2 over. Okay. If this were a full 64-bit number, what would happen to the bits number 62 and 63, the guys at the far left? They'd fall off the wagon. Okay. This partly depends, though, of what kind of shifting you're doing, because so there are actually multiple kinds of shifts. There's logical shifts, arithmetic shifts, and what's the third one? Um, rotate. Um, okay, so rotate, anything that falls off the end comes back around. And then logical and arithmetic. Logical, you just shift, and whatever falls off, well, sorry, sucker. Arithmetic, you say, okay, was the number that I started with negative or positive? Shift, but then make sure that the output number is the same sign that it needs to be. Um, and there are instructions for this in the assembly language. We'll talk about that, I'm sure, at some point. Okay, so all that's happening there is a 2-position bit shift. Okay, and the reason that it's a 2-position bit shift is because 2-position bit shift to the left is the same as multiplying by 4 in binary, And what was the difference between number of instructions and actual memory length of those number of instructions? It's a factor of 4, right? Because every instruction took 4 bytes. All right, does that kind of make sense? Oui? No. Très bien. Okay, let's make sure Jack's doing okay. Oh, what is that? Never do it. Okay, Jack says that he's never seen the bit shifting either. So, all right, well, whatever. Yeah, so it's a logical shift. Okay, and in fact, while we're at it, let's just go back to the bastion of all knowledge of Western civilization. Okay, left and right shift operators. Okay, just look up a reference. And I'm pretty sure it's pretty similar in Java. Be nice if this would go a little faster. So yeah. Anyway, that's all that's going on, just shifting. So you can shift one way or the other. Yeah. So okay. All right. So let's go back to here. All right. So that explains then why this immediate was basically A, not what we would have expected. Namely, what did we get? 2.8 in hex. Yeah. Okay, does that make sense? Okay, so that tells us where we're jumping to. Where are we dropping, boys? We're dropping to Rusty Routine 1. No? Okay. Yeah. And Fortnite would maybe be a lot more fun if there were programming jokes all over the place, right? Yeah. Okay. Anyway. All right. So that tells us that we're going to jump here. So what's going to happen is the program counter, when we hit this line, is going to be 0.8, right? And then the branch is unconditional, so it'll definitely happen. We'll take whatever our program counter is now, okay, which in the code looks like it's 0.8, but it, of course, might be different once the program gets loaded in memory. But regardless of that, how far do we need to jump past that to get to the desired instruction? That was the 2.8 in hex, right? So that's what we're going to tell the computer, but we'll encode it as that difference bit shifted 2 to the right. Okay, so how did we compute the 0A? Well, we actually did it backwards, right? So how did the compiler, the assembler compute it? It said, all right, you want to jump from instruction at address 08 to instruction at address 30. What's the difference between those two numbers? 2.8. What's 2.8 bit shifted twice to the right? 0A. So bam. Okay. There you go. And that's what you actually put in the encoding. All right. So now one of the benefits of doing this, right? Because we could have we could have, like, let's say we were ARM and we were designing this instruction set. Couldn't we have said, you just put the actual difference between the program counters in that immediate 26 field? We could have, right? What's the benefit of having this built-in bit shift? More range, okay? Because in a sense, we're getting 28 bits for the price of 26. Yeah, that's kind of nice. So that's the reason. Okay, good. So now we know where we were supposed to jump to. Yes? All right, so let's actually go through GDB and see what happens when we run this thing. In particular, if I run it, well, nothing seems to happen. Well, that's weird, because what should have happened? Some printing should have happened. Why didn't it? Well, let's find out. All right, so let's step. All right, step. That's what we'll, so let's do info registers, see what we've got. All right, so what do we got in our registers? What's in register 0? The number 3, that's what I chose to load in, okay? And then let's go down to all of our other registers here. So we've got X29, X30, the stack pointer, which we need to talk more about there, and our program counter happens to be this, okay, which was main plus 8 because we're now 2 instructions in, okay? All right, so let's pay attention to imagine that this started as not 8-0 but 7-8, right? That would have been 2 instructions ago, okay? All right, so now let's step again, okay? And we just executed that jump, or sorry, we're about to. Okay. All right. Now look at our program counter's value. Okay, it is whatever, right? But that's however many. What was the difference between where we started and where we ended up? So the difference should have been 2-2, or sorry, 2-8 in hex, right? So where were we a minute ago? We were at a bunch of 5, 7, and then what was it? 8-0, I think, right? Well, what's 8-0 plus 2-8 in hex? It would be A8, which is bam, exactly where we are now. Okay, so the offset was what it should have been. That's good. Well, can I keep running this thing? Right. All right. We're now into our subroutine. Okay. So I just did the doubling. Okay. And so look what we've got in register 0. I had preloaded it with 3, and so now it's 6. Great. All right. Now what? Program counters value. Oops. Okay. And so what's the next instruction that I'm about to do? The ret. Okay, so what's the return instruction do? Well, that's the sort of next piece of discourse. Let's see what happens. Let's just run things and see what happens. What happened? It ended. Why did it end? Yeah, okay. So what we've done is something naughty, okay? Namely that you can't branch to a subroutine and come back from that subroutine with just branch. You have to branch and link. Okay, so let's rerun this from the beginning. Okay, so what's the, before I've done anything, okay, so I have not executed any instructions in this program yet. Okay, and I know that because what is in register 1, or 0, excuse me, 1, right? And the second instruction I put in was to load that with the number 3. So we haven't hit that instruction yet. But if we go down, let's look at our program counter, okay? What's our program counter's value at the beginning? Okay, 5, bunch of 5, 7, 7, 8. Okay, so that's where the operating system loaded our program into memory starting at that address. Okay, and it's up to the operating system to determine where it gets stuck into memory, not us, because we're dealing with an operating system. Now in Brookshire, where would this have been? The very first instruction. 0, 0, always. Okay, but that's not necessarily true on a real architecture. Okay, so that would be the program counter's value at uh, the sorry, the at the beginning of the program. Okay, so what branching and linking will do is, so let me actually change, let me exit the debugger for a second, okay? And I'm going to make one very minor change to my main file. Instead of branch, I'm going to make it branch and link. Okay, so what would that do to the actual instruction that's here in my listing file? This dude right here, what would that have done? This 1 would have become a 9 because I've flipped a bit. That's all I've done. Okay. All right, so I did that. Let me reassemble it so we can rerun it. All right, so I want to do this and then that. Well, first off, let's watch this. Okay. Oh, I know why I did that. Yeah, it's interesting. Okay, whatever. So, let's GDB. Okay, and I'm going to break main. Okay. Let's see. There's nothing in registers yet because I haven't executed anything. Oops, sorry. Run first. Okay, so I just broke here at my store pair instructions to store. Okay, so let's look at my registers here. What's the program counter's value when I start the program? That, right? I haven't done anything yet. So I'm going to load in the instruction at that memory address. I'm going to execute it. I'm going to add 4 to the program counter, load in the next one, execute it, and so on. Good? Okay, so let's step. Okay, and let's do info registers again. Okay, so now what's our program counter? +4. Okay, good. Let's step again. Info +8. Okay, we see our program counter. Okay, look at X29 and X30 in hex. What do they start with? 7F and then a bunch of stuff. Okay, we just jumped into the subroutine like before, but this time I branched and linked. Look at X30 now. It's where we left off +4. Okay, so the link register is the register X30. And what that register will do is it tells us when we finish the routine, where do we go back to? Okay, well, should we have gone back to at the end of routine 1 finishing? We should go to the line right after we branch to routine 1. Okay, well, what is the memory address of that instruction? That's what's going to get stuck into X30. Okay, so when you hit the return instruction, it's going to say, okay, I'm going to branch unconditionally to the contents of register X30, which takes me back to the line right after I branched. Okay, so why did this program croak when I didn't have BL there, when I just had B? Well, it didn't know where to go, but it actually did. So let's change it back and see what happens. Okay, so, right, the only difference is the L. Oops. Okay, look at the link register now. Did the link register get changed? No. So the branch instruction doesn't change the link register. The branch and link one does. Okay, so the reason this program croaked is because the link register is that 7FF blah, blah, blah. So what happened when we hit the ret instruction in our subroutine? The return instruction is going to say, okay, change the program counter's value to whatever in the link register, which is this 7F blah, 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 and go there and start loading an instruction. But what's that memory address 7F blah, blah, blah? I have no idea. Is it our program? Probably not. Okay, because our program is at 555 and so on. Okay, so that's why the program croaked without the branch and link. Okay, you can't branch to a subroutine without linking. Or maybe better put, if you branch without using the link register, you can never come back from that routine wherever you jump to. Okay, so how many of you guys have seen the movie? I mean, maybe you guys are all too young for this. All dogs go to heaven. Yeah? You can never come back, Charlie. You can never come back. No? It's been a while? Okay. All right. And how many of you have never heard of or seen this movie? It's an animated movie from the 80s about dogs. It's actually a really cute movie, but it's sad in certain ways. So go watch it this weekend. Maybe not. Yeah.
So when we were in class, like last session or 2 sessions ago, and we branched to loop, it returned back to where we had it to.
Yes. Okay, so good question. So let's actually go back and look at that. Um, let's see, where did I put that? I think I had this one, loops one. Well, let me look at the listing file. Um, yeah, okay, so that's a good catch. I really should have had BL here, not B. Well, okay, this return is going to return to the operating system when the program's complete. Okay, so so that maybe is the better answer to what was that 7F blah 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 blah. That's some sort of like OS thing that we should be returning control to the OS after we finish running the program. Okay, so so what I should have done, I should have had a BL here. Okay, the reason it worked is because when I hit the end of the loop, this ret and that ret would actually have taken me to the same place because the link register never got changed. Yeah. Okay. And so that's why we wouldn't have noticed it in this particular program uh, because of that. Yeah. Um, so what should I have done is that this one right here should have been a branch and link right there. Okay, so let me open up that assembly file, the main one. Let's make that change. Okay, and then let's see it in action. Yeah. Huh? Oh, conditional branch and link. Let's see. Let's think about it. Uh, so yeah, branch, that's conditional branch, but no link. I don't believe you can do a conditional branch and link. I think what you would have to do is Well, let's actually just look at our reference here. Okay, so there's branch and link. We want conditional branching, conditional branch immediate. Um, no, that's interesting. I don't think there's a way to do it with a single instruction. Yeah, what you'd have to do is you'd have to have like say a branch and a branch and link, and then have this branch. If you don't want to do the subroutine, jump past it. Um, yeah. Um, no, I don't think you can do that in a single instruction, and which is kind of interesting, right? Um, yeah, Evan. For what? Doing a conditional branch that also linked? Um, well, like maybe you only want to enter the subroutine under a certain circumstance, like if x is greater than 7, then square it, otherwise double it or something. I don't know, right? My point though is that that's probably going to take two instructions, not one. Um, yeah. Okay. So no, fair question. All right. So let me recompile or reassemble the this loop program from last time, and let's see. Actually, you know what? Deliberately, let me change it back to what I had. So let's compare the difference between. So let's make it B loop, okay? And um, all right, so I need to do AS. Okay, and then all right, so let's do GDB. Okay, so break main. Oops. All right, so let's step, step, step. Okay, so this is right before we branch. Um, our program counter is here, and our link register is again this 7F whatever. Okay. All right, so if I step, I'm now inside the subroutine. Okay. And if I do info registers again, notice that my program counter's changed, but my link register has not. Okay, because I just did a branch, not a branch and link. Okay. All right, but let's step. Let me just go through it a bunch of times. Okay, we're looping, right? So it's doing the comparisons. I'm going to loop again. One more time, I think. Okay, there. So we're about to run the return command. Okay, good. All right, so notice our link register never got changed from what it was at the very beginning of the program. Okay. And now what happens if I step one more time? Garbage. Okay, yeah. Less than or equal. Okay. Because in that particular loop, we were basically just doing for I equals 0, I less than or equal to 4, or some whatever it was. Okay. But there are 16 different conditions that you can use for the conditional branch: less than or equal to, greater than or equal to, never, always, right? And then a whole bunch of other combinations. And you just, look them up. Um, okay. But yeah, pretty much any condition you could want could happen. All right. So what happened here? It croaked, right? All right, well, let's go in and change this back to BL. Oops. Okay, and I just realized actually I think will still croak if I do it this way, but let's see and find out why. Um, okay, so now that I'm inside the subroutine, let's see what our link register is now. Now look at the link register. What is it? It's 5 stuff, right? But that's basically the would be the line right after the branch in my main routine. That's where I want to go back to when I finish the subroutine, the loop subroutine. Okay, good. All right, so um, let's keep stepping until the loop's finished. Let me not be a dumbass here. Okay, so the loop just finished. We've done our thing, and now we're at the return instruction. And what are our program counter and all of that jazz? Okay, we're at loop plus 16, 4 instructions deep, and where are we going to pop back to? This address here in the next thing. Okay, so in the next instruction, the program counter is going to get changed to be the 728. Okay, good. All right, so let's step. Okay, now we've returned to the main routine, and now let's look at our registers. Okay, look at the link register and the program counter. Now, that's good, right? They're the same. That's what took me back to the main routine. Okay, what's the next instruction though? It's the return, but the return from the main routine, not from the subroutine. Okay, what's going to happen when I run this one? What's happening? Something's happening, or is it? Huh? Yeah, endless loop. Because what's the value of the link register? It's returning to the returning to the returning to the returning, and so my Pi is probably overheating right now. Huh? Yeah, well, actually, yeah, we can see that something's going on because look at the temperature gauge and the processor activity gauge. It's a quarter full, right? Which means the single core that this process is running on is at full utilization because I'm running something that's an endless loop that's not doing anything useful. Okay, so, and then I tell it to stop, and then hopefully our activity monitor drops off and our temperature will start to go down. Okay, so what do we have to do to fix that? Well, so let me quit here. Let's go back to our routine here. So what was the problem? Why did this happen? The link register was the same as where we were. Okay, what should the link register have been like? What did we forget here? What's missing from the beginning and the end of this program? Not stack pointer, but putting things onto the stack. Okay, so what's missing here is Is it minus or plus? That's what I thought. Okay. Believe me, I've made that mistake more times than I care to count. Okay, so what happens is that when the program starts, the link register, okay, we need to store its value from the beginning of the program because that's where we should return to once we're finished with the program to return control back to the operating system. Okay, so um, our branching instruction right here, the BL loop, changed the value of the link register. Okay, but we needed to know what the previous value of the link register was. Now, before I added in the store pair and the load pair, where was the information of the previous value of the link register? It was gone, right? Because I overwrote the link register and I never saved its contents anywhere. So the very beginning instruction is going to store x29 also, but in particular, x30 is the one that we really need to keep track of. It's going to store the very, very beginning value of the link register from when we started the program. And then right at the very end of the program, what are we going to do? Load it back out of memory. And now we can return control to the OS cleanly. Okay, does that make sense? Yeah? All right, so let's see this in action. Okay, so before we do anything, what is our X30? Blah, 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 D24. Okay. Um, all right, now that we're into our subroutine, what's our link register? 72C, which will be where we go back to when we finish the subroutine. Okay, so let me just keep stepping to get for the loop to finish. Okay, so we just hit the return, loop's done. We return, we're back to main. Okay. This is where we had the problem last time. All right, what's my link register? Where I just jumped back to. Okay, but what's the instruction that I'm about to execute? Yeah, I'm going to load the old value of the link register into X30. Okay, and so let's step, and now look what it is. It's back to the D24 that it started with. Okay, and so if I step one more time, what should happen? Because I'm now on the ret instruction. Um, well, it finished. Um, let me go back into GDB and let's just do run. Right, it exited with code 5. Okay, so it exited, it finished code 5. What was special about 5? That was the number that was in register 0 when we finished. Okay, so yeah, it kind of looks like we had a problem, but not really. The program correctly runs and terminates. Okay, that's I think more of a GDB thing than it is. Um, yeah. Okay. So that's why we have to push and pop the link register onto and off of the stack. Okay. Which means that, so where are we going to go with this? Well, um, we just talked about branch and branching and linking. Okay. The difference between the two. Uh, so we need to start really hammering this idea of the stack, and then also talk about, so Will's question, I think, in more detail of how would you do a conditional branch and link, okay, a situation like that. We also need to talk about register branching, but we got to quit. So, all right, I'll come up with some new fun assignment for you guys. How about that? Yay, assignments. Huh? In 10 minutes. I'm kidding. Okay. All right. Hope you guys have a good day. See you, Jack. Hope you have a good evening, whatever time it is there. And I'll see you guys next time.